And this distinction, this is something I may ask you on the final. So an easy recursive algorithm. So this is a fairly simple problem. They call them triangle numbers. Essentially, you have a right triangle here, hence the triangle name. And so we have a right triangle formed by x's. The question is for a given row, i.e. 1, 2, 3, how many x's are there in the triangle? T of 4. How many x's are in the triangle? There's 4, 5, 6, 7, 8, 9, 10. So f of 4 is 10. Does everybody see this? Now you might also notice this is the sum of n integers. I.e. f of 4 is 1, 2, 3, 4. But it's easy to express this as a recursive algorithm, and it's simple to follow and understand. All right, so f of 5 is 5 plus the rest of them. Yes? 5 plus the rest of them. Okay, so that is n plus the rest of them. So this is one way you count the integers 1 up to n, summing them. You can do it recursively if you want to. It's a simple idea. Okay, this does not work as a macro. It won't fly. Why? Because the expansion happens at assembly time, not runtime, but this is a runtime thing. So imagine that I ask for f of 5. Well, how do we use the system stack? Well, here we go. I'm going to say f of 5. So n is 5. I call this with n is 5. All right. So I start this bad boy here. This is triangle of 5. So I enter the subroutine as n1. No. Then what do? Return n plus triangle n minus 1. Okay. I enter t of 4. Now n equals 4, and it's on the stack. Is the 5 on the stack? Yes. You didn't pop it, you just pushed it. Okay, so we enter this, and is n1? No, it's not. So we come down here, and we have n plus triangle of 3. Okay, so on the stack, we push another call, n equals 3. This is the system stack. How many n's do we have in play now? There's 3 of them. N is 5, 4, and 3. I have 3 separate n's. How would you do this with a macro? You can't. Okay, t of 3. So we entered it with n equals 3, and we checked with n1. No. So we call t of 2. So when we call it, of course, we push it on the stack. Okay, finally, we enter this with n equals 2, and is it 1? No, it isn't, so we call t of 1. Okay, we've got 5 stack frames, 5 activation records, 5 different values of n on the system stack. Does everybody understand? We have started 5 methods, but not finished any of them. None of them are finished. So you can push lots and lots of things on the stack, And this is the way recursion works. We started but did not finish 5 calls. All right, here we hit the stopping condition. We hit the stopping condition and we return 1. Then we come back here. All right, the stopping condition. Well, here we're returning n plus triangle n minus 1. Well, okay, that's 2 plus n minus 1 is here. So what does that return? 3, yes. This is 2, n is 2 here, plus triangle of 1, 3. So we return and we're back here. All right, what's n? Because understand, as we finish, we pop. We finish, we pop. N is 3, it's the top of the stack, plus triangle of 2. Triangle of 2 is 3. So, we return 6. 3 is popped off the stack. N is 4. 4 plus T of 3. Well, T of 3 is 6. And 4, that's 10. The 4 is off the stack. 5 plus triangle of 4. Well, we know what triangle of 4 is now. It's 10. 5 plus 10 is 15. So now, all of those frames have been popped off the stack. That's how it works. Now that, of course, you can't do with a macro. It doesn't work. Okay, so that's one thing. Macros don't work for recursion. The other biggie is it can cause enormous expansion of the source code. Where we're doing exact literal substitution into the source code, it causes expansion. Some of you put down, a number of you put down all kinds of crazy things. And if I thought you did too much of it, then I took a couple of points off. But the shotgun approach really doesn't work on questions like this. The shotgun approach is write down everything you can think of and hope something is right. And the person grading it will see something right and think, oh, that's good, and move on. But if you write down 10 wrong things and 1 right thing, what am I supposed to do about the wrong things? So I can tell you what I do is take off points. So, okay. The macro, I think most of you got that. That was pretty easy. However, you couldn't put in m in there. That's not part of the expansion. If you did, you commented it out. You have to. The CPU doesn't know what an indim is. It's not a legitimate machine instruction. And then there was the hand translation, and you guys did pretty much across the board fairly well with that. So that was the exam. Do you guys have any questions about this? No. Okay. Yes?
What was full credit for
Number 3. Which one was that? Oh, the advantages and disadvantages. If you gave me the 2 biggies, I was happy with it. The 2 biggies meaning no recursion, and it can cause enormous expansion of the source code. I mean, I didn't need the Great American Novel here, just the reasons. Macros are commonly used, and the lower or closer to the machine you get, the more common they are. And there's nothing wrong with using them. In some cases, when you have really low levels, you use macros to hide from students subroutine stuff. That is, if you call a subroutine at the assembler level, there are 3 things you have to do. You don't just call the subroutine. You have to push parameters on the system stack, and then you call the subroutine, and then you have to pop the garbage off the stack. Well, for many beginning programmers, this concept of pushing parameters on the stack and then jumping is difficult. So we use a macro instead. Note that you can use the system stack if you want to in a macro. You certainly can do that. It's available. It's available to any part of the program. You can certainly use the system stack. And one thing that is fairly common to do is to save registers so that you don't have side effects. Save registers. All right. Other questions? Anyone? Okay. Good. So we're just about to the end of the semester here. Our final is a week from Friday, I guess. Is that right?
Mm-hmm.
All right. Do we have any questions about the program before I start talking about compiler stuff?
I do have a question.
Yes.
When we're calling the parameters inside the macro definition, for example, the \1 or 2, do we have to check if there is a \a to z as well?
Well, here's the thing. If there's a mismatch between the declared parameters in an invocation versus the definition, i.e. in the definition, maybe I have a \6, but when I call the macro, I only supply 5 things. Is this an error? Well, it is, but the assembler will catch it. And this is what the existing macro preprocessor does, and I don't have any objections. So if you have a \6 and you don't supply the parameter, then you're going to end up with something that looks like maybe this, move.w, d1 comma, and there's no destination. There's nothing there. So when you assemble the file, it gets flagged, and the assembler says, you know, error in syntax on line whatever. There's no destination. All right, you caught the error. That's fine. So do you have to match them all up and make sure that they're exactly the same? You do not. You do not. I mean, I could have given you the specifications that you have to do that, but from the beginning what I've said is it needs to work the way the installed macro preprocessor does, and that's the behavior it has. So you do not have to do that.
Okay.
So if you let it go through, and you know, in this case, if you have a \6 sitting in the code, and it didn't get replaced, for instance, the other scenario, and it didn't get replaced, this too would cause an assembly error. So it wouldn't get through, you don't have bad code, you get an error. So you go look at it and you go, oh gee. I mean, one of the problems that I have when I teach this class is the students sometimes don't use the macros correctly. And then they send me an email and they say, Mr. Riggins, I think something is wrong with one of your macros. Never mind that we've been using them for 10 plus years and I haven't found a bug yet. Not that I'm above having bugs in code, but they forget to use them, or they don't use them correctly to pass the wrong number of parameters, or the parameters in the wrong place, and then they don't work. And the problem is it's not their code. So they get this assembly error on line, 467, and they go and they look and they say, whoa, this is in one of Riggins' macros. And so they send me a note and say, something's wrong with your code. Would it be better if there was an error message that said incorrect macro invocation on line 12? Maybe. You can make the case for both, but that's the way it works. So I don't care if you don't implement that kind of behavior now. If you want to check them and error out before it gets to the assembler, that's fine. But if it does this, I'm happy with it. Yes?
So just to clarify, is it okay if we just stop checking until \9, or did you also want us to check \9?
Oh, okay, maybe I misunderstood the question. Do we need to allow \A, B, C, D through Z?
Yes.
I don't think so.
Okay.
I've done a lot of this stuff over a number of years, and I have never seen more than 9 parameters. In fact, I don't think I've ever seen more than 3 parameters. That's extremely rare. When I was a student taking 237 back in the early 90s, We had a project where the only solution was to come up with a macro that took a bunch of parameters. That was the program from hell. But even then, I don't think I used A through Z. So forget about that. I'm not going to test with that. I'm going to test it with real code. So if you process the includes correctly, you process those macros, and you do the expansion correctly, that's exactly what I want to see. But the A through Z thing, no, you don't need to do that. So I'm sorry if I didn't get your question correct. But that, no, 0 through 9 is more than enough. There are other switches that comes with this architecture, and one of the more interesting one is an assembler or a preprocessor directive, no macro expansion, so that it doesn't go to the listing file, but it goes to the executable. So you remove the macro expansions from the source code file. We didn't implement that, though, in the one we're using now. Other questions, anyone? Are you finding this fairly easy, or is it difficult?
The data structure part is the hard part, but after that it gets easier.
If you work out the data structure, I think that's true. If you work out the data structures, you get your mind around it, then it's not so bad. But work this out with pencil and paper, how you're going to store stuff and process stuff before you go for it. Because you might have, let's say you have key value pairs in a map. The key is a string, but what's the value? Well, maybe the value is a struct, and what does the struct have in it? Maybe it has a vector. And what does the vector have in it? A struct. Oh my, then things start getting messy. So if I have my map and I want to look for or find, and I've got Jeff equals, oh my goodness. So maybe M find, and what are you looking for? You get back, you pass in the key, right? So what's this? This has got all the macro stuff in it. What is it? So if this is a struct of some kind, so of course it wouldn't be struct here. Let's call it MCRO, macro. That's my struct. Okay, what's in that struct? Well, there's a vector, there's an integer, there's parameter vector. And this vector that has the lines of code has labels, opcodes, operands. Oh dear, well then how do you get to it? And arrow or dot. And what's the name of this vector? Call it V. Which one do you want? That's the first line. Label. All right, so you can see it can get confusing. Work this out before you start writing code and chasing your tail. Work it out first. What should it look like? How do you store it? And once you have your arms around that, then it's a fairly straightforward process. Okay, any other questions? Okay, some compiler stuff. So last time we talked about compiler optimization. Do we recall optimization? So, what's loop unrolling? I can see it on the final now. Describe loop unrolling. What is loop unrolling? Yes.
Where if you have like a basic for loop and it's doing something very basic, instead of actually having the loop, the compiler will recognize, oh yeah, it's just some very simple instruction that's being repeated like 100 times, for example.
Okay.
And it will basically say, instead of saying, like if it did I gets A or whatever, or I gets 1 or 2 or 3 or whatever, it'll actually unfold this 100 times.
So you have 100 lines of code instead of a loop.
Yes.
Uh-huh. Okay, I like it. Strength reduction. Strength reduction. What is that? Yes.
It's converting like multiply and divide to easier things like shift left and shift right.
Okay, use a cheaper instruction where you can. Sure. Absolutely. All right, I have some other goodies here. Branch elimination. What does that mean? You eliminate branches, okay. But what's the deal? How does that go? So, at the machine level, of course, that's what we're talking about here. If x is greater than y, then count plus plus. So just do this as a simple example. Okay, so many students would write this way. It's pseudocode. If x is greater than y, go to increment. This, of course, isn't machine code. You have to have if condition go to. So we have to have the go to instruction. There are no blocks. Go to skip it. Okay, if x is greater than y, you go to do the increment. And if it's not, then you're going to go to skip it. And then we have increment, count plus plus, and skip it. Is that right? Will it work? Can you follow this? Can you trace the route here? If x is greater than y, go to increment. Count plus plus, then on to the next line and out there. If x is not greater than y, it doesn't branch, and it goes to skip it. So does this behave the way it should? Sure it does. Is it good? No, it's terrible. Why? Because there are too many branch instructions. Yeah. X. Does that work the same way? If x is less than or equal to y, go to skip it. If it doesn't go, then we do count plus plus. Well, if it isn't less than or equal to y, it must be greater than y. Yes? Are you with me? Okay. So we have fewer branch instructions. This is branch elimination. You rework a block of code to minimize the number of jumps you want to make. Why does it matter? Why do you want to minimize the number of branches?
Faster.
Okay, well, what's wrong with branches? Jumping around in memory is not a good thing. It isn't always this case, and it's impossible to come up with generalities that always apply, but anytime you jump to a different location, you take the caches. The cache, C-A-C-H-E, is the set of instructions around where you're at right now. If you jump somewhere else, then that pool of instructions is tainted. And so if you keep hopping around all over the place, you taint the cache many times. The absolute fastest way to do code is no branches at all. If you have a program where you can remove all of the loops, all of the if tests, and replace it in its entirety with a sequence of instructions, one right after the other, that will run rings around any other kind of code, even if it's longer. It's faster. It's jumping that costs you something. All right. Loop collapsing. Loop collapsing. Okay, what does this look like? Loop collapse. Out. Let's just say stop. Have to do the stop information. So we got rid of the J. We got rid of the J. Constant folding. Constant folding. Okay. All right, it's a constant. So could you yank out the size times 4 and just put 400? Yes, you could. Code hoisting. What's hoisting? You lift something out and away. Yeah. So we might have or okay. So instead of doing that, would that be cheaper? Well, how many times are you going to do 2 times pi? first version. So you remove what you keep, so you don't do it over and over and over and over again. Questions so far? So I can tell you there will be a subset of these on the final. I'll ask you what they are. Register optimization. Okay. All right. So we don't have registers in C or C++. They exist. You can say register I if you want to. However, the compiler will not see that as anything more than a suggestion. And it's not recommended you try doing that. You should allow the compiler to figure out how it wants to use the registers that are available. But if you have a memory location, what is the difference between the two? Or register R 0, R less than count, R plus plus versus int I. Is there much of a difference in performance? So if you say for int I equals 0, where is I? Where is I? What's that? Well, maybe. Where do local variables go? Where are they allocated? The stack. Okay. So, is there a difference between access time for the stack versus a register? Well, where's the stack? Is that on the chip, the CPU? Where's the stack? Where's it kept? It's in memory. Memory that's not different. I mean, there's one pool of memory, and a certain segment of it is used for your stack and for your heap. Each process, every program that runs has its own stack and heap. Unless you've done something different, a system program might only have, for instance, a stack. But essentially, virtually all programs have a stack and a heap, and they all are in this pool of RAM. So what's the difference in access time between a register and RAM? Is RAM slower? Why is RAM slower? What makes RAM slower? Yes? Well, that's part of it. Yes, it's exactly what it is. That's part of it. What happens when you try to read I from memory? You put a request. I mean, there are different mechanisms that are used, but essentially you put in a request to read a segment of memory. That request goes to the memory controller. That memory controller identifies where that piece of memory is, and it sends the signal to fetch it. That memory is then fetched, placed on the bus, and sent back to the CPU. Okay, so it's fast. It is, in terms of actual, wall clock time. But in terms of the computer, is it fast? Not really. Why is it not fast? What makes it slow? Well, there are a couple of things. One, all the work that has to happen. And two, is the geographical distance and the topography. So if you open up a computer and you look, the RAM is not installed on top of the CPU. Where is it? Yeah, there are slots in the machine, in the motherboard. There are memory slots. Well, how far are they away from the CPU? It depends. Every machine's different, not that far. But that far, of course, in terms of computer, is huge. So how far can electricity go in a nanosecond? A billionth of a second. How far can electricity travel? Anybody know? Not like that? Something like that, I don't know. 6, 8 inches? Okay. So that's a billionth of a second, but a modern CPU can do 3 or 4 billion things in a second. So just the fact that you have to wait for the memory to be fetched, to be dispatched from where it is over here to where you need it here, is time consuming. I mean, it's kind of like, okay, I want some Mexican food. So I'm going to walk over to Roberto's. Compare that with getting on a plane and going to Mexico City to eat tacos. I mean, the difference is huge, right? Well, in terms of this miniaturization, when you've got something this far away, it's a very, very long ways away. Also, most CPUs, with almost all the registers, are part of the data path. And so they're already wired into the circuits that are going to do the arithmetic logical computations. So the performance difference is huge. Registers, of course, are a finite resource. We only have a few of them. And RAM is huge, and we got lots and lots of it. So there is a difference. So one of the things compilers can do is optimize the use of registers. That means looking carefully, where can I best use a register? And always use a register if you possibly can. But in a case like this, it becomes critical. So can we qualify this in some way? What do you suppose the performance hit is to read something from RAM versus read it all out of a register? What's the performance difference? Reading from RAM is how many x slower? What's the hit? 1,000 times as plausible. You have a super fast CPU, maybe a few hundred times. But it's really not likely better than that. Okay, so in the time you could do 100 to 1,000 things. In that period of time, you can, so for one memory read, you can do 1,000 things. Is that a difference? Yeah, obviously it's a huge difference. And of course, if you talk about memory hierarchy, memory is several hundred to 1,000 times slower. What's a hard drive? Oh heavens. Or hard drive's even slower yet. Figure another 1,000, at least. At least. Yes, I mean, we have solid state drives that are better, but they're still dog slow compared to the rest of the computer. I mean, if we talk about traditional platters and hard drives in general, they measure RPMs. A hard drive rotates. So if you have a hard drive that's, say, 15,000 RPM, some people think that sounds really fast, but isn't. So if you have to move the hard drive head, how many seeks per second can you do with the 15,000 RPM drive? What's that?
15,000 per minute.
Yeah, what do we measure per minute in the computer? Oh, yeah. So how many revolutions per second is that? What's 15,000 divided by 60? About 250? Okay, 250 things per second versus 3 or 4 billion things per second. Would you say they're slow? Yes. Right, so the faster you can get the information, the faster you keep going. What does a computer do if you ask for something from memory, or God forbid the hard drive? The hard drive's a different story. Anytime actually you ask for I/O, you get kicked off the CPU. That's a given. You understand with modern multitasking systems, they go round robin. Everybody gets a quantum of time, a time slice. You know, if you log on to Edoras, there might be 100 people using that same computer, but it looks like you're the only one using it. It doesn't look like there are 100 other people using that machine. How does this even work? The way it does, everybody gets a quantum of time. So it depends on a lot of factors what that value is, i.e. how long each time slice is and how often you get them. But everybody gets a time slice in round-robin fashion. And the general rule is if you ask for I/O, if you ask for input-output, you immediately kicked off the CPU and go into the wait queue, where you have to wait till the answer comes back. And when the answer comes back, then you assert a signal and let the CPU know that you've got your stuff and you're ready to go again. But you're going to get kicked off immediately. Why? Well, if it's going to take you a substantial amount of time during which the CPU could have done a billion things, obviously, you don't want to have the CPU sitting there loafing, doing nothing, if there are jobs that need performing. So you get kicked off at once, and then when you get your answer, you get a chance to run again. Okay, so optimizing the use of registers, and this is an example. If we're going to do a loop like this and we can't get rid of the loop, then by using registers instead of memory, it can be much faster. One of the big trends now in computer design is parallelization. We've started to hit a wall in terms of how fast we can make chips. Well, not started, we've kind of hit it. I think maybe 15 years ago, Intel was promising 4 gigahertz chips. And we still don't have 4 gigahertz chips. Yes, you can find them, they're expensive. Why aren't we on to 20 gigahertz chips or 100 gigahertz? Yes.
They found it was less power efficient to go above a certain gigahertz rating and just try to do more things at the same time rather than try to do faster.
Yes. Part of the problem is the nature of architecture, i.e. how do you make it go faster? You do that by making things smaller, because the limiting factor is how fast electricity can go. And so if you have electricity coursing through a chip, it only has one speed, as fast as it goes. So your clock cycles, though, are dependent on this, that sets the speed of the chip. But the speed of electricity is more or less a constant here. And so the smaller and smaller you make things, the faster and faster they can be. So we get smaller and smaller dies for the silicone wafers. But when you get to the point where you have circuits that are only a few molecules wide, how much smaller can you actually make them? And what happens too is as they get smaller and smaller, they tend to bleed electricity. They get super hot, and then they're not efficient. And so there's a limit. How much smaller can you make them? If you have a transistor that's only a few molecules wide, can you make it smaller? Not so much. So we hit this wall. And, you know, every time in computer science and science in general where we hit this wall and say it can't be any faster, well, of course it can. It's just not with that. I remember the big discussion 20 years ago was about how much faster we could make dial-up modems. You watch an old movie and you hear the tones going when they're dialing, and then you hear this ding ding, you know, the chimes as it's trying to negotiate communication with another modem, right? So they said, well, 28.8, that's the fastest modem you could have, 28 megabits. And they said, oh, well, we could go faster. Well, the faster they got them, well, they hit the wall about 56, and people said, oh,
It
no.
was only kilobits.
Kilobits, right, not megabits, kilobits, which is, you know, 1,000 of a megabit. So how much is 56 kilobits, 56,000 bits? Oh boy. How many, can we convert that to bytes? Megabits versus megabytes. How many megabytes is 56 megabits? Kilobits. Divide by 8. What does that give you? 6,000 or 7,000 bytes per second? Okay, I don't think you're streaming Netflix at that speed. No. 6,000 or 7,000 bytes? No. 6,000 or 7,000 megabytes, maybe, but megabits, of course, is not megabytes. So that, they said, was the theoretical limit. We couldn't do any faster. So I think pretty much everybody has faster internet than that. Even the wireless is much, much faster. But are we using dial-up modems? No. Nobody uses dial-up modems anymore. They're in the museums at this point. So they were right. There's a limit to what you can do with the dial-up modem. How fast can you send a signal over a copper wire? Well, gee, who cares? We moved on. So what happens with CPUs? Yes?
Switch to quantum computing and use light to transition the quantum states of atoms.
There you go. There are different things you can do, but the silicon substrate we use now is about at the end of its useful life, so we keep pushing the envelope and coming up with more and more things we can do. Intel has actually done some amazing work on their modern chips. They're really quite astonishing what they can do. But we're going to have a completely new technology to take this to the next level, and quantum computing is stopped looking like science fiction and started looking more and more like something viable. You know, another idea that I thought is interesting is biological computing. You can do this for instance, if you have exponential algorithms that can't be solved with the traditional computer, you can use biology with DNA sequencing, and you can do them all of the possibilities at one time. And they're so tiny, of course, they fit in a beaker. Interesting concepts, but it won't be the silicon that takes us to the next place. It's going to be something different. But one of the things that Intel has done, they have changed the architecture of these chips to try to maximize the throughput. Part of the problem is the long wait from RAM, so their first pass at that, we got L1, L2, L3 caches to speed that part of it up. And that helped a great deal, actually. That was a huge benefit. But it wasn't enough, and the next frontier is parallelization. So, all right, we already have parallel algorithms. We do. There are a number of different algorithms where you can break the problem up into chunks and give a chunk to a processor to work on, and then you combine the results. So for instance, if you need to search an enormous array, you have big data situation, you have terabytes, and you have to do a search. So if you split this up, you have, say, 2,000 CPUs, and each has 10 cores. So you got 20,000 cores, so you split it by 20,000 and give each core a chunk to search, then it becomes manageable. The real challenge, though, is taking sequential code and parallelizing it, i.e. the algorithms you write. How do you parallelize that? Well, it turns out that some things aren't interdependent. Other things are. You know, if you have int x equals y plus z, int a equals b plus c. Can I do those two things at the same time? Or do I have to do them one after the other? Is there any problem with me doing these in parallel? This in one core, this in another core, doing them at the same time? No, there are no dependencies. But of course, now if I have this, can I do those at the same time? Not so much, all bets are off. So the next challenge for designers, compilers, is figuring out how you can parallelize things. But right now, the CPUs themselves analyze the code string to see what they can parallelize. And the term is in flight. The newest chips can have as many as 60 to 80 instructions in flight, that is, in the queue ready to go, and then you do what you can do when you can do it. But you have, inside a single core, as many as 60 to 80 instructions going at once. So no instruction is one clock cycle, none. So if you have a 1 gigahertz computer, does that mean it's slow? Not necessarily. It depends on how many things it can do at once. So if you have a 1 gigahertz CPU and it can do a bunch of things at once, well, it works like this. Suppose you have let's say we have I1 and it needs 10 cycles. And we have I2 and it needs 4 cycles. And I have I3 and it needs 5 cycles. And I4 and it needs 4 cycles. If I do these all at once, is there a way that I can get it so that the average instruction is less than 1 clock cycle? Is that possible? Can I get it down so that the average instruction executes in less than 1 cycle?
Split it up.
You can if you've got 20 things going. Imagine I have 20 of these. I'm not going to write them all. 4 cycles. And I6 is 5 cycles. Okay, they all run at once. So after 5 cycles, what do I have? 1, 2, 3, 4, 5 things done. So I can actually average more than, or do less than, do more work than 1 cycle. So in this way, a 1 gigahertz computer can do more work than a 3 gigahertz computer that doesn't have as efficient or sophisticated a design. Okay, what else do we have?
Is that just threads or cores?
It's not cores or threads. It's part of the CPU. It has a instruction window, the single core, single thread, an instruction window that can accept. I don't know. The last one I looked at was the Haswell, and it takes 72 instructions in flight at once. Is the maximum. Of course, you have to have 72 that can go. That doesn't mean the CPU is going to be executing 70 instructions all of the time, but it can. So if you have things that it can parallelize, it will. Okay, let's stop there. Wednesday, I have some things on software engineering to talk about. Monday, then a week from today, is a final review. And what else is going on next Monday? Program. Good. Okay. So I'll see you guys Wednesday.